So let's talk about buffers and the network. It's perhaps not well known, but a network is actually comprised of a bunch of transmission elements, cables, and at the end of each cable segment is a switch or a router. And the way the router or switch is meant to work is stuff comes in, you look at the packet headers, you figure out where it's meant to go, you send it out. And certainly in the age of telephony or in even the age of ATM, that function was almost real time, that stuff came in, stuff went out. Why would you need to hang on to anything? Why is there memory? But oddly enough, memory is really important for data. Because what if you get 10 packets coming in that are all destined to the one output? Well, you can send one on, but what about the other 9? Sort of, oh, I'll drop them on the floor. That's not going to work. So somehow you need to be able to stage some of these packets and delay them and defer them so that you've got available time to send them out. But oddly enough, the memory in these switches serves a bigger function and a more important function than just statistical multiplexing, this collision of many in, one out. Computer protocols don't know how fast to go. Unlike telephone circuits, which went traditionally at 8 kilohertz or 8 kilobits per second, encoded, whatever, my computer can talk fast, it can talk slow, it can talk any speed. What speed should it talk? Well, the real answer is, it depends. How fast does your car go? Not can it go, does it go? Well, it depends on all the other cars on the road at the time. How fast does TCP go? Well, it depends on what else is happening. How do I know how to sense how fast I can go? Well, there's no one to tell me. So this is actually a practical experience. All of TCP does the same thing. Keep going faster and faster and faster until the feedback from the other end, the acknowledgements of my data, tell me I've dropped a packet. Oh, went too fast. Must slow down. So I drop my sending rate and try again. Send, acknowledgement. Send, 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 send. Faster and faster until I drop a packet. This is great. I've kind of got this loop now of accelerate and stop, accelerate and stop. But what if you had no memory in these buffers? The network's idle. I send a bit more, it's still idle. I send a bit more, it's still idle. I send a bit more, just a tiny bit too much. A packet gets dropped and I back off. But there's this huge amount of network capacity that isn't used. Now, TCP is greedy, or efficient if you want to use the other form of that word. Unused network capacity is a crime. So what I'd like to be able to do is to drive the network as fast as it can be driven. No idle time. Now, oddly enough, the way you do this is you have buffers in the switch. Because I don't just go until the other end's full, but I actually load up that buffer so that when I get a packet drop and I'm busy recovering, the buffer will keep the network busy. As it drains, I'll be reassembling my forces and then I'll be sending again and the line will be kept idle. So I've now got this model that says the protocol wants to make the buffer bigger, stop sending, let the buffer drain. Make the buffer bigger, stop sending, let the buffer drain. Almost like lungs. So when I'm not sending, those lungs are keeping, the rest of the next link active. So the net's full. This is what I wanted, okay? So how much buffer do I need? Well, the way we did this, we're simple people, was to make the buffer equal to the size of the link that it's driving. So that when you have a problem, you rate halve, and when you rate halve, the buffer drains into the line. And so the buffer equals the size of the link. Simple maths, easy to do. All wrong, as it turns out. Because what happens when there's two flows? or 3 flows or 4 flows. They're not in sync. Each one's running at their own speed with their own round trip time or delay. So they tend to interoperate in all kinds of weird ways. And having a buffer that's too big is just delay. And delay makes it slower, oddly enough, not faster. And so for years, we actually did buffers equal to delay bandwidth product. Wrong. You're just making things slower. What's the right number? Much, much harder to actually understand. A lot of work happened at Stanford University with Nick McEwen and that group over there. And there's a couple of landmark papers. The first is really quite old, 2004, that said, you know, hang on a second, maybe you should divide that bandwidth delay product by the square root of the number of sessions that are across that. Because the more sessions you're using, oddly enough, the less buffer space. 10,000 sessions, the buffer only needs to be 1/100th of the size. It's quite small. Why? Why is this actually interesting? Because inside switching chips, I've only got so much real estate. I can only put so many gates. I have the switching fabric, and if I can put memory on that same switching chip, it's really fast and really efficient. But that chip can only accommodate at most about 100 meg of memory. So if I need a gig of memory, I've got to put in memory controllers, interfaces, etc., and put the memory off in another chip. That's expensive, oddly enough, and to make it fast, it's really expensive. So this question about how big does the buffer need to be is actually a question with a lot of money attached. And if you can actually work the system so that I can build 40 gig, 100 gig circuits with less than 100 megs of memory on the chip, I've got a really cheap chip that goes really fast. And so we've been experimenting with protocols and hardware to understand that if this model of delay bandwidth product is wrong, and this whole idea of doubling and halving, which is TCP Reno, is wrong, and both of those are wrong. What we teach and what we think we know is all wrong. What's right? And this then gets into this idea that maybe we shouldn't be relying on buffers too much. Instead of sending rapid bursts of packets, we should gently pace the flow so that we're not stressing the first queue. But equally, packet loss is a disaster. What we actually want to know is when the queue starts to form, not when the queue is full. Because if you know when the queue starts to form, you can actually react even on tiny queues when it starts to form. So there are a couple of protocols out there, and a lot of folk are working on variants of this that now use techniques known as pacing and various forms of delay management in the line protocols that actually change that flow. And I suppose the realization is that we can actually go a lot faster than we're going today and a lot cheaper than when we're going today by simply changing the way we structure the protocol that sits on the wire. If you want to read more about this, have a read around Google's BBR protocol, which is one of the better examples in the last couple of years on this different way of thinking about how we engineer both the hardware and the software of the network.